This is the continued commentary for the Chapter 347, Acetal, Ketal, and Carbohydrates handout. In this handout, we will talk about biomolecules pertaining to carbohydrates, we'll talk about stereochemistry, and we'll talk about identifying key stereochemical points such as enantiomers and stereoisomers. First off, biochemistry. So this is your first section where you deal with biomolecules. Biomolecules are any type of molecules that are found in life, such as a living cell, for example. They tend to contain carbon, nitrogen, oxygen, and hydrogen. And here is a pie breakdown of the different percentages. You're not responsible for memorizing the numbers. This is just for you to look at. But biomolecules are found in life. A big difference between biomolecules and organic molecules is you don't necessarily always have to have carbon present. For example, this is a phosphate molecule. Notice it has no carbon present. However, it is important in the processes of life. So there are many inorganic molecules which are considered biomolecules. So without going off on a tangent, let's go ahead and focus on one class of biomolecules, the carbohydrates. Now, in this set of slides, we only talk about carbohydrates. So even though it says Chapter 7 will focus on carbohydrates and lipids, you can cross out lipids. There are 4 classes of biomolecules. Just as we have classes of organic molecules, acids, aldehydes, alcohols, we have classes of biomolecules. Proteins, carbohydrates, lipids, and nucleic acids. Biochemists, they tend to break these down more by function rather than by the functional groups. But they tend to break it down by function in the body. Or function within the cell. So right now we're just going to focus on carbohydrates. These are the sugar molecules. So living organisms break down carbohydrates to release energy, but carbohydrates are also used as a molecular structural component, providing the framework within cells, for example, or the framework for DNA, for example. So they have many purposes other than being broken down for energy. So going to the slide. So in this slide right here, carbohydrates tend to always have carbon, hydrogen, and oxygen. They also tend to have a lot of alcohols present on them. This is an example of a monosaccharide, a single unit sugar molecule. This has a specific name we call glucose. Now, we previously talked about hemiacetals, and we compared those to cyclical or closed chain hemiacetals. So this is important because we see this occurring in living cells and sugar molecules of living cells. So in this instance, I have a open chain glucose, and what will happen is one of the alcohols, just as we studied earlier, will go ahead and do a backside attack on an aldehyde. The alcohol will become the ether, as seen in this closed chain molecule here, and the aldehyde will become the alcohol, this particular molecule right here, or this particular functional group right there. So again, this occurs in biochemistry on a cellular level all the time. Now, nature does this because there are times when it wants to use the sugar for energy, and there are times when it wants to simply store it, or at least store it temporarily. The open chain form is the form that is broken down for energy. The closed chain form is the form that is used as a temporary storage form. And finally, carbohydrates are not only used as energy, but they're also used as structural components, and they also make up the chemical antennas, so to speak, also known as antigens, found in the body's intercellular communication. So moving on, here are more examples showing the open chain form and then the closed cyclical hemiacetal forms. Notice if you have a cyclical hemiacetal formation, you can actually have different alcohols which can react, creating multiple different closed form isomers. On the left hand side, we have glucose, open chain and closed form. On the right hand side, we have ribose, open chain and closed chain form. Now, the possibility of creating different isomers is immense. We can create many different types of isomers. However, every cell is very picky and it only wants one type of isomer. So often what biochemists do is they have a naming scheme referring to that one type of isomer, since the other isomers are not existent in a living organism. So this one type of isomer has the name glucose. This other one has a name ribose. So this summarizes what I just said earlier. Open chain, energy, closed chain, temporary storage. Let's move on. Some other general classification schemes. Monosaccharides, aka simple sugars, refer to these molecules right here. Disaccharides, di meaning two, means you have two sugars and they're linked together by a ether functional group. In biochemistry, we refer to this as a glycoside linkage. A glycoside linkage. Disaccharides have their own unique biochemistry common names. In this case, this one right here is lactose. Lactose. Now, when you have multiple sugar units connected by these glycoside linkages, when you have many sugars, we call this a polysaccharide. Poly meaning many. So, oftentimes, when the body is not using sugar, it will sit there and store it in this form right here, compacting the sugar units into a polysaccharide for, albeit a little bit longer storage, until it's ready to be used. Sticking with this classification, you'll be responsible for giving the open chain monosaccharide classification name. So just as I asked you to classify ketals, acetals, you'll be classifying carbohydrates. There are two parts to this classification name. The first part, which I'll highlight in yellow, is going to either be aldo or keto. Aldo makes reference to a aldehyde functional group. Keto makes reference to a ketone functional group. So also known as ketosis in biochemistry. So going to this example right here, this carbonyl group would be a ketone in organic chemistry, so we refer to this as a keto. The second part of the name refers to how many carbons are present, as circled with my blue pen. So in this case, 1, 2, 3, 4, 5. If there are 5 carbons present, then the second part of this name is going to be a pentose. So the open chain monosaccharide classification name for this is a ketopentose. Let's go ahead and apply this to that handout that I've given you. So if you go ahead and you take a look at, for example, B, the CHO is actually a short naming scheme for an aldehyde. So in this case, the first part of this name would be aldo, because there are 3 carbons, carbon 1 up here, carbon 2 in the center, carbon 3 on the bottom. Then this would be tri, and the open chain monosaccharide classification name would be aldotriose. Aldotriose. So